Welcome to this explainer. Look, we're jumping straight in today because we are looking at something incredibly uncompromising. It's highly technical, completely devoid of hype, and honestly, it's critically necessary in the age of autonomous systems. We are talking about Rathnone. Now, to be clear, this isn't just another multi-agent framework orchestrating a bunch of helpful bots. Not even close. Rathnone is the ultimate, cryptographically verifiable cage for autonomous financial agents. Think of it as a sovereign finance gateway. It wraps these agents in a strictly deterministic control plane, meaning absolutely zero economic action executes without first passing an independent, unyielding authority layer.
Which brings us to the foundational axiom driving this entire architecture. Cognition is probabilistic. Authority is deterministic. I want you to really absorb that for a second. The persistent, dangerous architectural error we're seeing everywhere in autonomous systems today is treating a model's reasoning as permission to act. Rathnone explicitly severs that connection. Reasoning simply does not equal authority.
Because the reality is, a confident model is not an authorized one. A hallucinating model, or even a highly capable, mathematically accurate model, might propose the absolute worst possible financial action. It doesn't actually matter how smart the AI is. The model's output is never, ever authorization.
So here is our rigid architectural blueprint for the explainer today. 1. The threat matrix. 2. The epistemic spine. 3. Cryptographic armor. 4. The V4 failsafe. And 5. The operator console.
Let's kick things off with Section 1, the threat matrix, and dealing with probabilistic danger.
Look, if you just let an autonomous financial agent loose, the inherent risks are literally catastrophic. Without a hard boundary, a single LLM hallucination quickly turns into a totally drained treasury. So enter the meta invariant, known as M0. It strictly states that no security invariant depends on model behavior. Import walls guarantee that cognition simply cannot escalate authority. The whole system operates on this core assumption. The model might be actively malicious, or it just might propose the worst possible action. So the governance substrate literally cannot import the cognition layer. The separation is absolute.
Let's map out the trust transition sequence here. It goes Step 1, cognition, Step 2, proposal, Step 3, authorization, and Step 4, execution. This is a rigid sequence. It ensures that a proposal carries zero authority into the execution domain. The AI, it stays strictly in Steps 1 and 2. It proposes. It never ever decides.
Moving to Section 2, the epistemic spine, and how we get deterministic control.
The core component actually enforcing this boundary is a frozen, model-independent function called fleet.epistemic.decide. This is what dictates all consequential actions in the fleet. It's a pure, deterministic function. No random number generators, no external network calls, and absolutely no input from the AI model anywhere on its path. It is the uncompromising core of the system.
The spine takes the identity, the grant, and the scope, and it returns a hard verdict: auto, human, or blocked. But crucially, consider the epistemic data evaluated, things like the model's confidence score or its reasoning logic. That value is strictly zero. The spine returns its verdict without ever checking what the model believes.
Up next, Section 3, cryptographic armor and layering our defenses.
So the epistemic spine is necessary, right? But the surrounding cryptographic constraints are what actually lock the cage. Let's rapidly run through these safety invariants. First, no live signing without an auto verdict. Second, key-free verification using only the tenant's public key. Third is the panopticon defense, meaning no identity binding. If there's personally identifiable information in a live payload, it's immediately rejected. Fourth, AOM-independent verdicts, so capital size cannot dictate permissions. And finally, replay protection in a default deny state. And remember, these bounds are enforced even if an auto verdict is reached. The system just doesn't yield.
Then you have narrowing risk engines enforcing failed closed deployment bounds. Consider a real environment variable like Rathnone max settlement value way set here to 0.5 Ethereum. If an agent tries to settle above this mathematical ceiling, the system outright refuses to sign it. Doesn't matter what the model says, doesn't matter what the protocol says, it is a hard, fail-closed wall.
Let's contrast the deployment tracks to see how this builds out. You've got the default simulator track, which is safe by default. Simulated is set to true, there are no real signatures, and zero network egress. Then opposed to that is the opt-in live track. Here, live is true, and it's producing genuine SecP 256K1 or ED 25519 signatures for actual live settlement. It's a hard, explicit division between pretending and actually signing real financial transactions.
Now track this mutable audit ledger timeline with me. In Epoch 1, the proposal is logged. Epoch 2, the human approval is signed. Epoch 3, the action is executed. And in Epoch 4, the tenant-scoped ledger is updated. This isn't just a plain text log, you know? Signed human approvals have to mathematically bind to the exact artifact hash. If someone tries to reuse, forge, or mutate an approval, the cryptographic chain just rejects it instantly.
All right, Section 4, the V4 failsafe, also known as the operator antidote.
So what happens if the system is functioning perfectly, but we just need to pull the plug? Well, this is the ultimate defense mechanism, designed specifically to prevent the system from becoming an uncontrollable, immutable cage. A simple post to/safety/halt trips the circuit breaker. Live signing stops instantly. And a post to/safety/resume clears the breaker, but that requires explicit human operator action. It basically grants the human operator an independent hardware-level halt switch.
This breaker overrides fleet.epistemic.decide. The loop just stops. It halts live signing independently, completely ignoring whatever the AI model or even the deterministic protocol is saying. It really is the ultimate human antidote to the immutable cage.
Finally, Section 5, the operator console, our control room.
Bringing all this deep cryptography back to the human operator's reality, we use a Next.js control panel. We step sequentially right through the flow. Step 1, tenants. Step 2, authorize. Step 3, audit. Step 4, trace. And Step 5, safety. This is not just some basic UI. It's a direct window into the deterministic state of the agent's cage.
And the console guarantees an uncompromising foundation. An independent verifier recomputes the state, you get cryptographic trace evidence, the evaluation is strictly fail-closed, and the whole thing is verifiable by public key alone. This dashboard is built on an immutable ledger that simply cannot be deceived. The executor's success isn't trusted, it is mathematically proven.
As we wrap up this explainer, I want to recite the manifesto one last time, just to solidify the uncompromising architecture of this sovereign finance gateway. The model proposes. The protocol decides. Cryptography verifies. The ledger remembers. It's a stark, powerful, and absolutely necessary reality for the future of finance.
Which leaves us with a pretty chilling final question to consider about your own agent architectures. Your agent is confident, but is it authorized? Thank you for joining me on this explainer. Now, take a really hard look at the systems you're building